I'm excited to discuss how electrophoretic NMR, or eNMR, can be applied as a tool to characterize ion and solvent motion in concentrated electrolytes, and ultimately tying the solvation structures that we can observe back to macroscopic transport properties such as cation transference number. So of course, I have to acknowledge that my work is supported by the Joint Center for Energy Storage Research, which is one of the energy innovation hubs that's funded by the US Department of Energy. So as an outline for this tutorial, I will first discuss the background underlying the migration of charged species in concentrated electrolytes, and in particular to motivate why we need to selectively quantify the transport arising from specific ions. That is, to understand the transport properties of the cation rather than the anion, and also the role of the solvent, which nominally it's uncharged, but plays an important role. So this work is fundamentally motivated by how we might use electrolytes in lithium-ion batteries. So that forms much of the focus of the application of this technique. After that, I'll dive into electrophoretic NMR itself, which from this point forward, you'll hear me refer to as eNMR. This is still a relatively underutilized technique, and I would say that the instrumental and analytical infrastructure for doing these kinds of measurements is not that widespread. So I'll go into detail about what these measurements actually entail, as well as some of the pitfalls one can expect to encounter when working in this field. And that will likely be a good point at which to break for any questions. And from that, I'll move on from methodology to a more applied case study, showing how we can combine eNMR data with molecular dynamics simulations to really pinpoint solvation structures and how that directly impacts the transport of charged species. And so, this type of joint methodology provides a more complete accounting of ion and solvent transport. And my hope is that this not only allows us to understand why some ions move faster than others, but ultimately to design new tailor-made electrolytes where, for example, we might be able to selectively enhance cation motion at the expense of the anion. And finally, I guess I need to note that eNMR is a technique that did not originally develop with the purpose of studying lithium-ion batteries, since arguably these measurements existed in some form before commercial lithium-ion batteries did. Originally, eNMR was brought to bear on a host of problems in physical chemistry and biophysical chemistry related to colloids, micelles, counterion condensation, migration of charged macromolecules. I would be remiss if I failed to mention that, but as my focus is primarily on different systems, I hope the audience will excuse me if I simply say that there's excellent prior literature on using eNMR in those areas. So to motivate the importance of concentrated electrolytes, we can take a look at the scientific background on the 2019 Nobel Prize in Chemistry, which of course was awarded to Goodenough, Whittingham, and Yoshino for their work on lithium-ion batteries. In the official write-up, you can find an acknowledgement of some of the prior work on electrolytes, and in particular the work of John Newman, who was a professor at UC Berkeley who developed concentrated solution theory back in the 1960s as a means of modeling the transport processes in electrochemical cells. And for a binary electrolyte, which comprises one type of cation, one type of anion, and a solvent, the transport parameters that ultimately matter are these three: ionic conductivity, salt diffusion coefficient, and the cationic transference number. Of these, ionic conductivity is the most familiar, certainly the easiest to measure, but this T+0 cationic transference number is proving increasingly important, in particular in the current development of batteries. So what is the cation transference number? Well, we can conceptualize it as the fraction of current that's carried by the cation in a uniformly concentrated electrolyte. The 0 in T+0 emphasizes the reference frame for this property is with respect to the solvent, and I'll talk about that in more detail. And it turns out that this transport parameter impacts the formation of concentration gradients within an electrochemical cell, which is the major limiting factor to how rapidly a battery can be charged or discharged. And to motivate the importance of developing materials that can be charged or discharged quickly, none other than Claire Gray, of course, was quoted recently saying that fast charging is the outstanding research question that will determine electric vehicle adoption, rather than the questions that we typically ask about capacity or vehicle range. So I want to provide some more direct context for why transference numbers are important in battery systems. I'm showing here a simple model of a battery containing an anode, an electrolyte, and a cathode. And in particular, this electrolyte comprises a salt that is both cations and anions that are dissolved in a solvent. So this electrolyte, can be liquid or polymer, but the point is that there are nominally both cations and anions that are capable of carrying current. So the lines here depict salt concentration profiles that build up in the battery when current is drawn through it. These profiles correspond to the same state of charge, but different current densities. If the current density is low, the concentration gradient is relatively shallow, and the salt concentration is non-zero everywhere. But at a sufficiently high current density, the concentration gradient becomes extreme enough that this concentration can drop to zero within the region of the cathode. And that has significant consequences for performance. In particular, it limits the ability of the cathode to provide its nominal capacity. It also promotes irreversible degradation processes that will limit the battery lifetime. So the parameter that most strongly affects the formation of these concentration gradients is the transference number. And in particular, it's the concentration dependence of that transference number that allows for the prediction of these concentration profiles as a function of current density. Okay, so I mentioned the transference number, may be thought of as the fraction of current carried by the cation in a uniformly concentrated electrolyte. It may not be obvious how that even relates to concentration gradients or why the transference number has this 0, which is with respect to solvent. So to understand this, I want to briefly introduce the Hitorf experiment. And this figure is also taken from a recent paper on this subject. So in the Hitorf cell, we have 2 large anodic and cathodic chambers filled with electrolyte, each facing a non-blocking electrode. And they're connected in the middle with a narrow channel that allows for transport of the electrolyte between the 2 chambers. So what we do in this experiment is we apply a constant current. After a certain amount of time passes, we close the channel and measure the concentration within one of the chambers, in this case, the anodic chamber on the left. So when current is flowing, there are 2 different processes that occur. First, we're oxidizing the electrode and forming cations that enter the chamber directly, which increases the salt concentration. But we know that because this is an electrolyte that is under the influence of an electric field, some of those cations will be carried away from the electrode and leave the chamber, right? So this second process is actually determined by the transference number. And this is shown in the equation here, where the transference number enters into the second term, which relates to the number of cations that leave the chamber. So if all the current is carried by the cations, then all the cations that enter the chamber from the electrode also leave the chamber. There's no change in concentration and no concentration gradient that can form. But usually we don't have electrolytes that have a T plus of equal to 1. They have a transference number much less than 1, in which case there will be an increase in the salt concentration because not all of the current is being carried by the cations, and so not all the incoming cations leave the chamber. So the subtle point here is that it's not only the movement of the cations that affects the salt concentration. We can also imagine a situation where the solvent leaves the chamber with some of the migrating cations. And the result of that will also be to increase the concentration in the chamber because there's less solvent there. That is captured in concentrated solution theory, where the transference number is defined with respect to solvent. We can also write this as a ratio of the velocities of the cation, the anion, and the solvent species. And so just to clarify, these velocities here that I'm writing are the instantaneous velocities that would result from applying an electric field in an electrolyte of uniform concentration. They are averaged across all the cations, all the anions, or all the solvent molecules, regardless of the underlying speciation. So having a slow cation velocity here will lead to a small transference number, but also having a fast solvent velocity would have the same effect. And it's somewhat hard to fathom that the motion of a nominally neutral species has a large impact on the electrochemical transport, but I hope that showing this Hitorf experiment provides an explanation for the way in which solvent motion can also affect concentration gradients and also impact T plus 0. So the takeaway from this thought experiment is that in order to characterize the transference number, the ideal technique that we would want would be one that could separately characterize the species velocities of the cation, of the anion, and of the solvent. So now, despite how important transference numbers are to understanding battery performance, they're very difficult to accurately measure. This leads to a divergence of results within the literature, even on the same systems. This plot is showing 3 different ways in which transference numbers are commonly reported using different techniques, and how these numbers differ for the same electrolyte, which is lithium TFSI dissolved in polyethylene oxide. It's a polymer electrolyte. So by far the easiest measurement to make is that of the current fraction rho plus using the Bruce-Vincent method. This has small error bars, but because of some underlying assumptions about the ideality of the electrolyte, it turns out not to reflect the other transference numbers except in the dilute limit. Often, the transference number will be reported with respect to the mass averaged velocity, denoted T plus m. That's a rigorous and correct value, but it's presented in a different reference frame than one would obtain from electrochemistry. This is sort of the reference frame that you obtain from molecular dynamics simulations. And finally, T plus 0 is the transference number with respect to the solvent velocity. It's a fully rigorous variable. It has predictive value in understanding battery performance. But as shown here, there's frequently large error bars shown here in gray in the reported values because many different electrochemical techniques are typically combined in order to obtain T plus 0. So what this emphasizes is that we really do need to develop new techniques that can get at this parameter more directly with smaller errors. And ultimately, we want to be able to tie that to the solvation structure of our electrolytes. You may have noticed that on the last slide, the values of T plus 0 at some concentrations were negative. And I want to reassure you that you have the right to be confused about that, because there are reports in the literature that T+0 can be small or even negative in numerous systems, concentrated aqueous electrolytes, polymer electrolytes, and also mixtures of salts with ionic liquids. So if this situation occurs more frequently than we expect, we want to understand fundamentally what molecular factors give rise to small or negative T+0, so that ultimately we can choose or design electrolytes that have much larger, or at least non-negative cation transference numbers. So T+0 can be negative. One way we can conceptualize this is by the existence of these charged ion clusters, such as this triplet species that comprise one cation and two anions. So if the dominant mechanism by which the cations move is a cluster like that, then the effective motion of the cation will be as if it's negatively charged, and that would be sufficient to give rise to a negative T+0. But as you might expect, these types of solvation structures have remained elusive. There's not much hard experimental evidence to show directly that these exist. So what kind of techniques can we use in order to be able to probe cation-anion clusters in electrolytes? Well, we want to use techniques that can selectively probe the transport of cations and anions. Pulsed field gradient NMR methods are an excellent example of that. I want to highlight some of the recent prior work that I've been involved with. We, in collaboration with the Coates group at Cornell, prepared this series of systematic polyacetal polymer electrolytes. And what we did in this series was to vary the number of these ethylene oxide or methylene oxide units in the polymer backbone. And we quantified that using the ratio of oxygen to carbon atoms. So what we hoped here was to be able to map out structure property relationships for this series of host polymers. And the reason we wanted to do that is we found that electrochemically, the oxygen-rich materials, shown here in red and pink, have much higher current fractions, which is an indication that they may selectively transport lithium cations relative to the electrochemically inactive anions. And so then, surprisingly, using lithium PFG NMR, we didn't find much difference amongst the materials regarding the cation diffusivity, but there was a major decrease in the anion self-diffusion coefficients in the most electrochemically interesting materials. So on its own, PFG was not enough to confirm the relative mechanism of ion transport. So we had to turn to Raman spectroscopy to corroborate our suspicions here. And what the Raman spectra show is an additional feature corresponding to anion-rich clusters that form in the most promising materials, shown here in red and pink. And ultimately, from this complementary approach, we're able to say that the increase in the current fraction is likely tied to formation of these anion-rich clusters, which PFG NMR tells us are moving more slowly, meaning that the cations, relatively speaking, are moving faster. So the whole reason that I'm bringing this up is PFG is obviously an incredibly useful technique. It's one of the few techniques that we can use to get specific information about cations, anions, and the polymer backbone. But there's still a disconnect between the information that PFG can provide and electrochemical results, because while PFG is, of course, very useful, it's inherently not an electrochemical technique. And to really drive this point home, I want to consider two hypothetical systems in which correlated motion exists between different components of the electrolyte, and to consider the effects upon the transference number in each case. So many electrolytes exhibit some kind of a preferential association between the cation and the solvent. For example, these solvate ionic liquids, and in which case we might expect that the solvent and the cation motion is coupled in some way. So that would mean that the species velocities here are comparable, and thus the transference number is close to 0. So alternatively, the formation of cation clusters, as I discussed before, may render the dominant cation transport mechanism in the form of these asymmetric, negatively charged triplet species, and some MD simulations do support these claims. So then the cation velocity may be negative in that case, or at least less positive than the solvent velocity. And again, that would lead to negative or small transference numbers. So it's clear that solvation structures underlie T+0. But what can PFG measurements say in those two systems? Fundamentally, what we need to be able to say is something not about diffusive motion, which is inherently not directional, but rather about migration under an applied electric field, which is clearly directional. So in other words, in the two examples that I just discussed, in the first case, we would need to obtain direct information that the solvent drifts with the cation, which is not necessarily given by the result that they have similar diffusivities. And in the second example, we don't have information that the cation moves in the same direction as the anions rather than vice versa. Okay, so the solution to this quandary is to perform pulsed field gradient measurements, but with a synchronized electric field. And that allows us to quantify both the direction and the distance that species travel. And this is what we refer to as electrophoretic NMR. And for full characterization of a binary electrolyte, we'd like to quantify the species velocities of the cation, the anion, and the solvent. And for typical systems of interest, it suffices, therefore, to do lithium, fluorine, and proton eNMR measurements. So given that motivation for the importance of eNMR measurements, let's now consider some of the basic aspects of actually carrying out the technique and what we're actually quantifying. So practically speaking, we need at least 3 pieces of equipment that you may or may not have. One of them is a high voltage amplifier that synchronizes with the NMR spectrometer. We need some kind of a sample holder containing electrodes that allows for applying electric field pulses. And then, of course, we need existing instrumentation for performing PFG NMR measurements. And so just considering the broad strokes picture in the beginning, we know, of course, that we can use magnetic field gradients to localize the spatial positions of nuclei within the sample container. That's how PFG and MRI work. But by applying an electric field that's aligned with the magnetic field gradient, what we do is induce an ion migration. And that migration has an average distance. And I'll show that we can quantify that as a phase shift of our resonances. Of course, NMR also provides the spectroscopic specificity that we need to be able to probe different species or even minor components as long as we have the required spectroscopic resolution. So diving a bit deeper, we can understand how directional migration in the sample gives rise to a phase shifted resonance. In particular, look at this simplest spin echo PFG experiment. What we do in this experiment is we first label the spatial positions of the nuclear spins with a directional field gradient pulse. And then each spin acquires a phase in relation to its spatial position, which is typically depicted as the spiral of phases shown here. We then wait for motion or drift during a fixed period, often called the diffusion or the drift time. Then ultimately, at the end of the sequence, what we're going to do is apply a gradient pulse to reverse the phase information. Right, so if a spin moves during this period, at the end of the sequence, it acquires a phase in proportion to the distance that it migrated. And in this case, what I'm showing is a uniform flow. That means that all the spins acquired the same phase. They add together to give a single phase shifted resonance. And so in general, though, we don't observe that. We observe an average phase shift, which corresponds to the mean migration distance averaged across all the detected nuclei during the experiment. And we can contrast that with more typical experiments that probe self-diffusion. In typical NMR spectroscopy, we care about chemical shifts. In PFG, we measure signal attenuation. But eNMR is this kind of unique situation where we need to be able to quantify a phase shift of the signal. That's the quantity that we need to measure. So in a diffusion experiment, you can see here there's no directional motion. So the positive or negative phase shifts that would result from upwards or downwards motion simply cancel, and we merely observe attenuation. But in the case of eNMR, the phase shift is the quantity that we observe and need to be able to quantify. Okay, so diving a little bit deeper, the pulse program that's most commonly used in eNMR is a double stimulated echo sequence. And the main reasoning behind the choice of the sequence is to avoid measuring convection. In fact, any process that doesn't depend on the sign of the electric field is one that we want to eliminate. So the most straightforward way to do this is to utilize a convection compensated sequence. And in that situation, the pulse program is split into these 2 halves in which we apply a positive and then a negative electric field in sequence here, shown in red, and that's referred to as a bipolar electric field pulse. So then through phase cycling, we can obtain phase shifted spectra that represent the difference in the 2 halves of the sequence. So in other words, if we have a convective flow that remains constant throughout the sequence, its effect will be canceled. But any flow that does depend on the sign of the electric field pulse is constructively added together. Okay, now by changing the length, little delta, and the strength, G of the PFG pulses shown in blue, we're changing the migration distance that we're sensitive to. And as for the electric field pulses themselves, you can see that we apply 2 pulses of opposite polarity to induce the ion drift. They're typically on the order of about 10 or 100 milliseconds and a few volts per millimeter in amplitude. And at the end of the sequence, of course, we're going to measure our NMR signal as an FID. After Fourier transformation, we obtain a spectrum. And what's special about the spectrum, its peaks will be phase shifted in proportion to the average distance that the nuclei moved. By quantifying that phase shift, we can directly measure the migration distance. So what are the typical distances that we can measure? Well, they vary from tens of nanometers even, in the slowest cases up to microns. And it's a drift distance that's directly determined by the strength of the electric field pulse that we apply. We're intentionally going to keep that electric field pulse short, less than 100 milliseconds, not only to ensure that the concentration of the electrolyte remains uniform, but also to avoid degradation, sample heating, electroosmosis, more complex convection effects. And some limitations are listed below, but typically what we try to do is perform experiments in a regime where we minimize these artifacts as much as possible. And in the prior literature, you may see eNMR data reported as ionic mobilities, but for this tutorial talk, I'm going to instead report velocities at a fixed electric field, which are equivalent, but a little bit easier to understand intuitively. And one aspect of these units that's very helpful is that if we consider a qualitatively good electrolyte that has a total ionic conductivity of about 1 millisiemens per centimeter with a concentration of 1 molar, then the ion velocity summed across all the mobile species should be about 1 micron per second when the electric field is 1 volt per millimeter. That's kind of an intuitive unit because 1 volt per millimeter is a typical field you might find in an actual electrochemical cell. If you want to know how that's equivalent to a mobility, the units are given there. And finally, it's also worth noting that every eNMR experiment is also a PFG experiment because it means that both diffusion and attenuation occur at the same time, right? So diffusion leads to attenuation, whereas migration causes the phase shift that we want to quantify. Diffusion and migration occur at the same time. So typically what that means is we want to perform a PFG experiment first with the electric field switched off so that we know what range of gradient parameters we should apply in order to be able to observe signal and not over attenuate the phase shift resonance. So there's this natural trade-off between these two processes, right? Because we want to apply strong enough gradient parameters to induce a large phase shift, but not so strong that the signal to noise ratio is really adversely affected by attenuation due to diffusion. Okay, the other major difference between PFG and eNMR is, of course, the hardware. And while for the most part we're using commercial equipment in our work, I'll say that very little stops motivated groups from developing or modifying their own hardware, especially producing their own eNMR cells, because these are effectively just standard 5mm NMR tubes that have been modified to incorporate palladium or platinum wire electrodes. And unlike many other normal electrochemical cells or batteries, we have this very significant interelectrode distance, which implies the use of very high voltages in order to be able to reach significant electric fields. So some kind of high voltage amplifier is necessary that can rapidly switch electric field pulses on the order of tens of milliseconds, and in a way that we can synchronize it with the NMR console. And we do this through TTL triggers that are accessible through pulse programming. Finally, we want some way of connecting the amplifier and the electrodes of the cell, ideally in an air-free way that allows us to study air-sensitive materials. And so in this setup, the top electrode is removable, can be put back in position after loading the sample in an air-free environment. And this PTFE coupling here ensures that this remains air-free after reintroducing the cell back to the ambient atmosphere outside the glove box. So the RF filter and high voltage adapter here shown on the right links the electrode pins with the high voltage cable that comes from the back of the amplifier. Here you can see the brass adapter resting on top of a typical solutions probe. You wouldn't normally see this because it would be inside the magnet, but the point of this is that the adapter also acts like a normal sample spinner. It localizes the part of the sample that you want to study to within the RF coil, and we do it in such a way that the electrodes of the cell are outside the RF coil. And by the way, the bottom electrode here is fused into the glass, and there's a thin wire that runs up along the outside. It's connected to a pin that ultimately interfaces with the high voltage adapter. So as I said, that kind of an electrode arrangement ensures that the electric field is uniform within the sample. Of course, we need to apply rather large voltages of up to or sometimes in excess of 100 volts to drive ion migration, especially in samples that are not very ionically conductive. And what we don't want to do is apply a higher voltage than we need and cause sample heating or degradation. So the maximum voltage is typically dictated by how conductive the sample is. In any case, the electric field pulses that we use are relatively short, and we wait a very long period of time, typically a minute or longer between application of these pulses. And finally, it's also possible to apply the electric field pulses in either a potentiostatic or a galvanostatic mode. In principle, there's not too much difference between these, but the galvanostatic mode may be beneficial in cases where it's difficult to calibrate the electric field, for example, where you don't have a very well-defined interelectrode distance. And so you either need to perform some kind of a calibration first if you're using potentiostatic measurements. Okay, so as you may expect, there are a whole host of artifacts that can accompany a measurement like this. So I'll just walk 2 or 3 of them that I think are kind of critical to consider before you analyze and fully trust the data that come from eNMR. Probably the most important problem is convection, which is nominally compensated for by using the double stimulated echo pulse sequence, but which occasionally still manifests itself with this additional attenuation beyond what would be expected or observed with the electric field switched off. So here are some example proton eNMR spectra that I acquired looking at the migration of the tetramethylammonium cation. The only difference between these is how long the period between the electric field pulses was. And so you can see with the much shorter recycle delay, there's both attenuation and line shape distortion, which renders it very difficult to reproducibly determine what the phase shift of this resonance is. And so when we consider the mechanism for that artifact, the main origin is local temperature differences that result from the electric field application. And that gives rise to natural convective flow. And so the easiest method to account for that is to ensure that we have sufficient delays between the pulses to equilibrate any temperature hotspots and to ensure a uniform sample concentration. We can also minimize the applied voltage, in other words, just applying the minimum that we need in order to observe a phase shift without causing any attenuation artifacts. There are other sources of error that also can occur. They arise from what's known as electroosmosis. It's a phenomenon that does depend on the polarity of the electric field, and therefore we wouldn't necessarily expect it to be compensated by the pulse program. It relates to motion of the double layer at the boundary between the sample container and the electrolyte. It usually manifests as some kind of a plug flow. Fortunately, electroosmosis takes some length of time to build up. It's believed that by keeping the length of the ion drift period short, 100 milliseconds or less, that this can be minimized. And again, that will, cause the drift distance to be smaller, and it will make it harder to resolve any phase shifts, but it might be necessary. And finally, if one is uncertain if the results are reasonable or even the right order of magnitude, comparing to ionic conductivity of the sample is a great idea, because the ionic conductivity ultimately quantifies the sum of the velocities of all the ionic species. So it provides a benchmark by which to compare the velocities that we obtain from eNMR of specific ions. Oh, and finally, I would be remiss if I failed to mention that there are extreme measures one can take to prevent convective artifacts, in particular loading the sample into an array of capillaries and positioning this between the electrodes inside the eNMR cell. It's the approach taken by the Schoenhoff group, pioneered by them, and used by many of the groups that actively perform eNMR of highly conductive or highly convective systems. So in my work, I've encountered an alternative method of avoiding convective artifacts and ensuring reproducibility, and that's to perform the phase cycling out of order. So typically in eNMR, what we do is to vary the applied voltage, U, and then collect multiple spectra for phase shift analysis. But in my experience, some of the greatest spectral artifacts are observed from repeatedly applying the same voltage over and over again after each scan, whereas one could avoid this by switching to a different voltage or stepping through a list of voltages in some well-defined way. So to do this, though, one has to perform the phase cycling last. And to make this slightly more explicit, in a typical experiment, you might collect 8 scans, sequentially stepping through the phase cycle table, and then change the applied voltage. But in practice, it proves better to alternate voltages. And after completing a pair of positive and negative voltages, or some sequence of voltages that often includes a reference spectrum without applying any voltage, to then step to the next entry in the phase cycle table, and then repeat this process for the number of scans that one wants to collect. So this method also has the advantage if there's any field drift or long-term process causing artifacts, it sort of affects all the spectra equally rather than just affecting spectra acquired at early times or for some voltages rather than for others. And this is important because, as we'll see, eNMR requires comparison of spectra in order to determine a relative phase shift. Finally, I'll just note that at least in Bruker topspin, at least with the pulse programming that exists prior to topspin 4, I believe, this NBL keyword can be used to store sequential FID data on the spectrometer before eventually writing it to disk after completing the phase cycling. Okay, so one last artifact I want to discuss before launching into the data analysis relates to spurious or fake phase shifts that may be observed in a way that characteristically does not depend on the PFG gradient parameters that are used. It's precisely because these phase shifts don't depend on the gradient parameters that they can be identified as spurious and accounted for. So I mentioned earlier that the cells that we use have some components that lie outside the cell, namely a copper wire that connects the bottom electrode to the high voltage adapter at the top. Of course, this is a current carrying wire in a magnetic field. So you might expect parts of it vibrate or move during the measurement. And that vibration likely causes a change in the tuning and matching of the RF circuit. For those of you who have retuned your probe even slightly from one experiment to another, you know that that can cause a phase shift in your spectra. Usually you don't care about it, but it matters more in this case. So in particular, because the motion in some sense depends on the position of the wire, by adjusting the wire, we can in fact change the sign of the apparent phase shift. So that's shown in these example proton eNMR spectra of a carbonate solvent, in which the phase shift initially appeared to be one direction, but then by reorienting the wire, the phase shift changes sign. One way to minimize this issue is by fixing the wire in place so it can't move. But in practice, though, it's easier to average the results of pairs of experiments where the gradient strength is positive and negative. So just to reiterate, spurious phase shifts are likely caused by Lorentz forces on any current carrying components of the cell, in particular where they're perpendicular to the external magnetic field. That's not a process that matters for the ions themselves because the drift distance is parallel to the external B0 field. As I mentioned, one can actually eliminate these artifacts because they don't depend at all on the sign of the magnetic field gradient. So by averaging results in which positive and negative gradient strengths have been applied, in principle, the spurious phase shift can be canceled. And at the very least, one needs to check for this type of artifact before analyzing phase shift data. All right, so once we've collected phase shifted spectra that we believe to be representative of ion migration distances that we trust, how do we go about analyzing them? And this is a non-trivial question, not just because there's no standard software or analysis technique that one can really apply directly for this problem. So I'll present the method that we've used, which to my knowledge is unique, while noting the literature is full of other methods as well. So on the left, what I'm showing here is the raw fluorine NMR spectra obtained on an electrolyte, where this peak corresponds to the fluorinated TFSI anion. And first, one can only ever calculate a relative phase shift. So typically what's done is to compare two different spectra, one of which is recorded with no electric field, shown here in black, and a second spectrum where an electric potential has been applied, here shown in red. So the first step here is to make sure these spectra are aligned, meaning that we've accounted for any significant drift of the external field between the measurements. Otherwise, a field drift can mask itself as a small apparent phase shift. So to check that the spectra are aligned, what we do is we display the spectra in absolute magnitude mode so that the phase information isn't relevant or doesn't affect the appearance. And then we just align the peak maxima of interest. And that's already been done here for these spectra. Okay, the second step then is to calculate what we refer to as the phase spectrum. And I think a lot of us will recognize that when we display NMR spectra, we're only showing the real part of the spectrum. There's also an imaginary part that exists because we perform a complex Fourier transform on the FID. But that means for each frequency in the spectrum, there's both a real and an imaginary component. And that means it's possible to calculate a phase angle at each frequency. So if we calculate the phase at each spectral point, we obtain the phase spectra shown here. And what we can then do is more easily visualize the phase difference between these spectra. And so we just calculate the difference between these. In particular, we're interested in the position corresponding to the peak maximum. So you can see here that the phase difference between these spectra was plus 16.5 degrees. The minimum resolvable phase shift in eNMR depends a lot on the signal to noise ratio, but typically it's not smaller than a few tenths of a degree in the best case situation. So now I just mentioned that it's important to perform experiments with positive and negative magnetic field gradients. So here's the same experiment where I just switched the sign of the PFG pulses that I applied. So the phase shift should, in principle, be opposite of the top case, but in practice it differs slightly due to the Lorentz forces that I mentioned. But by averaging these results, we obtain a phase shift where the spurious effect has been canceled out. We can repeat this procedure at multiple different applied potentials, and what we obtain is a linear fit. And what that means is that the anion migration distance is proportional to the applied field. That's what we expect in the absence of convection or any other artifacts. That's really what we're looking for here. And also each phase shift can be directly converted to a migration distance. It turns out that with these particular parameters, plus 13.8 degrees corresponds to an average migration distance of plus 0.73 microns. Okay, so what do we do then? Well, we repeat this entire process for a series of gradient strengths, G, gradient pulse lengths, little delta, and electric fields, just to gain confidence that the velocities that we measure don't depend on any of these parameters. And what we do is to plot the phase shift versus all of these things. A linear fit here is going to give us confidence that we're measuring bona fide ion migration, and the slope of this best fit line is directly proportional to the ion mobility. It can be converted to an ion mobility if we divide by the length of the electric field pulse that we're applying, as well as the gyromagnetic ratio gamma. And then, of course, we have to convert from degrees to radians in that case. So as I mentioned before, I'm going to choose to write the mobility values here as velocities at a fixed electric field of 1 volt per millimeter. So the upshot is that we can say that the anion in this system migrates with an average species velocity of minus 3.57 microns per second at an applied field of 1 volt per millimeter. And so what we can then do is take all these velocity values and use them to directly calculate transference numbers. But of course, before I get into that, I just want to wrap up this section of the talk on eNMR methodology, and I'd like to emphasize the best practices for eNMR measurements. In general, here our goal is to avoid artifacts and degradation while still maximizing the magnitude of the phase shifts that we measure. So to this end, always use a long recycle delay, ideally longer than 60 seconds to avoid significant sample heating. For similar reasons, keep the drift time short and the maximum electric field small, although of course both of these also lead to smaller phase shifts. We want to perform phase cycling last and make sure to acquire reference spectra with the electric field switched off. And finally, check for any spurious phase shifts that result from the, with the electric field on, but that seem independent of the other gradient parameters to account for systematic spurious errors. Okay, and I should say at this point that for anyone who has worked with spectrometer peripherals and trigger pulses. At some point, managing the cables running out of the spectrometer becomes a secondary concern to these other points. And you know that if you have a spectrometer with two oscilloscopes on top of it, something interesting is probably happening in that lab. So I just want to point that out. And I should also really say that all of this work just builds on the existing methodological developments that many other groups have developed over many years, and particularly the Stilbs group, the group out of Virginia Tech, Lou Matson's group, and Monica Schoenhoff's group. And I want to highlight that these really important papers have driven the technique forward to where it is today. So I think at this point, I'm happy to pause for questions if there are any before I launch to the final part where I show how we can actually apply this to a real electrolyte system.
Okay, that was fantastic. It's a real tour de force of the methodology, and it's nice to see how you've overcome what is clearly a lot of problems. Please, if you have any questions, write them in the chat. I can kick us off. So you talk about the ion moving almost like a fixed difference, but presumably, there's always a spread. Not all ions will migrate the same amount. Is that effectively what you're calling diffusion? Will it lead to a spread of phases that will result in a decay?
Yeah, that's a good point. So there's two different processes. I mean, the spread of, how wide that spread is what's going to cause attenuation, right? So ultimately, you can think about this as a profile of distances, right? And if that profile is very wide, we're going to have a lot of attenuation. But if that profile is centered at, let's say that profile is centered at 0, meaning there's no net migration, well, then the phase shift will be 0. But if that velocity or distance profile, right, is centered at some non-zero value, then it'll either be a positive value, in which case we get a positive phase shift, or it'll be negative, in which case we get a negative phase shift. And for sure, because the time scale of this diffusion or drift time is so long relative to all the processes that can occur, we're just going to be averaging across all the different speciations that might exist in the electrolyte. And that's something that I'll get into a little bit more in the last part of this talk, where I sort of discuss how the simulation work can inform what the solvation structures are.
And just to finish up on that, so the apparent sort of diffusion, the amount of decay is going to be larger than if you just did a PFG experiment that just measures the diffusion.
That is an excellent question. I believe the answer to that is yes, because it will cause an additional spread in the migration distances. But I guess you have to keep in mind as well that typically the diffusion, this is a little bit non-intuitive. Typically the diffusion distances are much larger than the migration distances. So when we calculate what diffusion mean square displacements exist, we're talking about microns, but typically in eNMR we're dealing with much smaller distances. So it's sort of a smaller effect on top of, migration is a smaller distance on top of the existing diffusion distance, if that makes sense.
Okay, I wouldn't have guessed that, but
yeah, it's sort of non-intuitive, and I didn't really have a chance to go into it, but it relates to the fact that it depends on the square of the gradient in PFG, but it's linear with the migration, the phase shift's linear with the gradient in eNMR, which is kind of a subtle point. Yeah.
Okay, cool. So we have a question from Thomas Osman Pop, who says, "Hi David, great talk. Regarding voltage incrementation and then incrementing the phase cycle, do you see a difference between random ordering of the voltage increment versus sequential or monotonic incrementation?"
Yeah, that is a really good point. It's not something that I've sort of systematically studied in that way. I would suspect that if you were to run a very long experiment where you were sequentially incrementing the voltages like that, I expect that in some systems you are going to see degradation, and if you do that in a way where you're degrading the sample either early on or later, then yeah, you're gonna see artifacts related to that, and you'll at least by doing it randomly, that effect is scattered throughout the data rather than just like I said, confined to early times or later times. But I know I haven't really studied that systematically, but that's a good question.
I was also curious about your sort of out of order phase cycling. Are you sort of stable enough that your phase cycle works, that you're actually looking at the same thing by the time you come around to cycling the phase?
I believe so. I wonder if part of that has to do with these very long recycle delays that I'm using. And the other thing is, as far as spectrometer instrumentation, the stability of that, if we run the same experiment, at least with the electric field off, we don't see phase shifts of larger than like a tenth or a couple tenths of a degree. So it seems to be, as long as there's sufficient signal to noise, that this works, and you can resolve small phase shifts, even though you have a very long period between the steps in the phase cycle.
And do you lock? Just as a very
no, we haven't locked. I mean, that would be a much more elegant solution than what I've done here. But we would need something to lock onto, and we don't always have that available because we're studying the electrolyte as a whole rather than dissolving it in a deuterated solvent. Yeah.
Okay, interesting. Okay, in the interest of hearing the rest of this talk, I'm going to hold back the rest of my questions and looking forward to the last bit.
Okay, great. Well, hopefully we'll have a little bit of time to do some questions at the end. So I think this part will be relatively short. So I just want to show a case study where we've actually then used this technique to probe a particular electrolyte system. And in particular, we've also used simulation methods in parallel to investigate a concentrated electrolyte. So I've already discussed the underlying methodology of eNMR, which is shown on the left. But on the computational or the molecular dynamics side, here shown on the right, what we did was to use this recently published equation that links molecular dynamic simulations to the Onsager transport framework. And in particular, what that means is we're going to be calculating Lij coefficients that characterize correlations between species I and J, for example, between cations and anions. This is a calculation that's done under quiescent conditions. There's no electric field actually applied during the simulation, but the term here in brackets is an average correlation function. It sort of, in some sense, can be represented as a mean squared displacement. So the transport coefficients are then proportional to the slope of these effective mean squared displacements over time. And so in this plot, what we're showing is MD simulations performed by our collaborator, 2 different salt concentrations, and we're using the MSD data over which we observe diffusive motion to quantify this Onsager transport coefficient L++, which captures cation-cation correlations. We want to get these coefficients because we can then use them to directly calculate properties like conductivity, like transference number. Okay, so now to validate the hybrid experimental and computational methodology, we're targeting this model system of lithium TFSI salt dissolved in tetraglycine. It's chemically similar to polyethylene oxide, which is a very common polymer electrolyte. And using eNMR, what we've been able to do is to characterize the average species velocities of the cation, the anion, and the solvent in a range of electrolytes with varying concentrations. And also throughout this section, R is a measure of concentration that's often used in the polymer electrolyte space. It refers to the ratio of lithium cations to the oxygen atoms on the tetraglycine solvent. There's 5 atoms on tetraglycine. And so note also that the anion velocity here is plotted on an inverted scale, slightly different scale bars, just so that we can more clearly see what's going on with the other species. But the anion velocity is negative due to its negative charge, whereas the lithium cation velocity in blue is positive, and it's smaller than the anion at all concentrations. So now, perhaps surprisingly, when we measured the induced drift of the nominally uncharged solvent using proton eNMR, it's not 0. What we find is that the solvent velocity in the laboratory frame is positive. So this result directly tells us that the solvent is drifting in the same direction as the cation, and also that these velocities become comparable at high concentration. So in order to make a comparison to molecular dynamic simulations, we can calculate these transference numbers from both experimental and computational data. And using eNMR, we can calculate transference numbers directly from all 3 species velocities as shown by this top equation. We need all these velocities, including the solvent velocity, which is not something that's usually considered or directly measured, but with eNMR, we can actually start to get some insight into. So what we can then do is compare the eNMR data with predictions from MD using the Onsager transport coefficients. We need to convert to the solvent reference frame using the mass fraction of the solvent and the anion so that these data sets are in the same reference frame. But once we do that, promisingly, what we see is this quantitative agreement between the 2 data sets with an error and also similar trends. So what we see is that initially the transference number starts out, typical value of about 0.3 or 0.4, and it approaches 0 at this critical salt concentration, which will become important shortly. So notably, this is the concentration at which the cation and the solvent velocities become comparable, right? So what we now have is a system with this interesting concentration-dependent transference number, and using molecular dynamics, we have some way to understand what's going on at the molecular level. So for the rest of this, I'll focus in on the MD results that have allowed us to pinpoint the origins of the changes in the transference number. To uncover the relevant solvation structures using MD, we first focus in on the local environment of the lithium cation. So lithium may be solvated by oxygens either on the tetraglycine chains, here shown in blue, or the TFSI anions shown in red at low concentrations the average number of tetraglyme solvent molecules near lithium is 2, but at high salt concentration, that decreases and the number of anions coordinating to lithium increases, right? So what we can then tie this to is the presence of two different solvation motifs that we see in the simulations. This two-chain motif comprises one cation and two solvent molecules. It's predominant in the dilute limit, but in the concentrated regime, we start to see more and more of these one-chain structures, which comprise a cation, a solvent molecule, and an anion. Our goal really, though, is to understand what's going on with the solvent motion in the context of these different structures. So in other words, how much solvent is coordinated in one of these structures compared to the free solvent. In the dilute limit, so that's what's being shown here, in the dilute limit, most of the solvent is not coordinated. So meaning that these values are relatively small. There's not much solvent in the two-chain or the one-chain motifs. But the fraction of solvent in the two-chain motif continues to increase up to this critical salt concentration. Then it decreases slightly. And so, the reason for this is beyond this point, there's not enough solvent in the system to fully solvate all the lithium that we've been adding. We need to bring in the anions that can also do some of the job of solvating. And therefore, we see this increase in the fraction of solvent in the one-chain motif. And so actually, we can understand this critical salt concentration as the point at which the number of lithium cations is exactly half the number of solvent molecules. That would lead to a prediction of this happening at R equals 0.1 because there's 5 oxygens in tetraglyme. And that's not too far off from where we actually see this maximum at about 0.08. Okay, so now when we overlay the eNMR solvent velocity data, what we see is that this actually trends pretty well with the two-chain solvent fraction, has a similar maximum at the critical salt concentration before it drops off. And so what this is aiming towards is we're going towards a mechanism by which to relate changes in solvation structure to the solvent velocity and then to the transference number. In particular, what we can see is that the maximum amount of solvent will be dragged by the cation in this two-chain motif at this salt concentration. And that concentration is the one in which most of the solvent is tied up in solvation shells. And in turn, that results in a minimum in the transference number. So we can use this quantitative solvation information to support a simple model of solvent motion. In particular, our goal here is to measure the solvation shell velocity. We want to just see if we can quantify, say, the velocity of just this particular motif. So this snapshot of our molecular dynamics simulation at high salt concentration shows the existence of different solvation structures. In particular, it lets us visualize the origin of the solvent velocity as arising from the dragging of the solvent by the cation. We can think about the shell velocity of these different motifs and how that contributes to the average solvent velocity, right? So in particular, in this simple model that we've proposed, only this motif should move under application of an electric field because it's the only charged species. This one-chain motif is neutral, just like the free tetraglyme chain. So in this simple model that we're proposing, it should have zero velocity and contribute that to the average solvent velocity. So we can then calculate a quantitative value of the solvation shell velocity just of this species, combining the eNMR and the MD data. So what we're going to assume here, as I mentioned, the solvent velocity that we measure is an average of some of the solvent in migrating solvation shells, some solvent that's not moving when we apply a field. What the MD results give us is the fraction of solvent in this migrating motif. We assume that's the only contribution to the solvent velocity. So that what we can then do is take the eNMR solvent velocity that was measured and divide it by this fraction to calculate the velocity of this shell. So if the hypothesis is correct and this model is right, what we're expecting to see is that the shell velocity and the cation velocity from eNMR should trend similarly. So when we make this kind of a comparison, we see that the values are similar with an error across a range of concentrations. So that means that the cation migration is directly responsible for moving the solvation shell, since the cation is the charged component of this structure. Okay, so what the simple model tells us is it validates our ability to measure the solvation shell velocity and tie this to a specific migration mechanism. So finally, armed with these insights, we can go back to the very beginning and kind of revisit the molecular underpinnings of transference numbers that I discussed at the start of this. So, I mentioned previous studies in the literature have often invoked negatively charged cation-anion clusters, but what we can see is that at least in this model system and at these concentrations, this is not necessary to rationalize low T+0. So in this system, we can justify low transference numbers through cation solvent coordination alone. And in particular, we can see that in electrolytes where this is the dominant solvation structure, the cation and solvent velocities are similar, and the transference number will be close to 0. So in short, this shows that burdening of the solvent by the cation is a sufficient molecular explanation for low transference numbers in these kinds of electrolytes. This work is also a clear example of this quantitative agreement between experimental and computational techniques, such that the eNMR velocities can be interpreted by reference to the results of the MD simulations that are pinpointing the local structure of the electrolytes. So to sum up, I want to give you some of the key takeaways of the power of eNMR, and I also am excited to talk about some future methodological directions that I think will further advance this technique. So first of all, I hope I've shown that quantifying the selective motion of ions in electrolytes is really important. eNMR is one of the few techniques that directly permits this. eNMR spectra have this characteristic that they have phase shifts that we can analyze. We have to use these to quantify the average distances of the migrating ions. These typically correspond from tens to hundreds, or maybe up to a micron of drift distances. But with this technique, we need to be particularly wary of sources of error. In particular, there are other sources of phase shifts that arise from spurious or real but undesired flow motion, such as natural convection, other flow artifacts, Lorentz forces. If we take care of these artifacts, we can start to resolve some interesting phenomena, such as solvent motion, which in fact, as I just showed, dominates the changes that we see in the transference number at moderate or high concentrations. And through MD simulations, we start to gain insights into why the species migrate the way that they do, which ultimately should enable us to make and use better electrolyte systems. So other systems of interest within the electrolyte space, are multivalent. People are interested in things like magnesium and zinc. That will prove a real challenge for eNMR, but I think somebody should try to do that. There's also the opportunity to go beyond binary electrolytes and look at more complex systems with different components. I say complex, but the most common battery electrolytes already contain mixtures of solvents. That's already a system that we have yet to fully characterize with a technique like this. And finally, there's the space to look at single ion conductors to determine whether transport is actually dominated by one species or how much other species contribute to the conductivity. So what I'm even more excited about, though, is what can be done in the eNMR space regarding methods development. There's been some work from the Blumick group, and I'm sure from other groups, looking at velocity flow profiles by magnetic resonance imaging techniques, but I'm not really aware of this being done with eNMR in a systematic way that you could compare with concentrated solution theory results. There are analogies to diffusion tensor imaging that I think are not really explored yet. And moreover, all of the methods that I talked about here are concerned with what happens initially at time zero, the instantaneous velocity when we switch on the field. But we know that the species velocities change significantly as the concentration gradients build up. So it would be really interesting to probe the velocities as a function of time. But finally, I think the most interesting space from the spectroscopic point of view is the development of maybe double resonance or NOE type methods that would selectively probe the solvation structures that I just discussed. And one of the challenges I think with that is the intermolecular NOE is not necessarily well understood, in the sense there's been contention in recent years about how to interpret intermolecular NOEs. But if you were able to do those measurements and interpret them correctly, I think you could actually more directly measure the velocities of some of these solvation structures. So in short, I think there's plenty of work to be done by folks who are motivated to expand this technique, make it even more relevant to study electrolytes in ways that are not just of academic interest. So with that, I just want to, of course, briefly acknowledge the Balsara and Reimer groups who have made Berkeley a very enjoyable place to do research. My funding, which comes from J. Caesar via the US Department of Energy, and then technical assistance was provided by Pavel Yushvanov, who is at P&L Scientific in Stockholm. So thank you to everyone for your attention. I'm happy to take further questions if we have the time.
It's nice to see the application, see it all tied together. So again, keep adding questions. So one question that came in just at the end of the previous question session from Kyungin Park, who says, thanks for your great talk. Do you think it's possible to measure the mobility of ionic surfactant micelles at very low concentrations, like millimolar concentration?
Well, I can say I don't have that much experience with micelles, but one of the interesting things about very dilute systems typically is that they have greater mobilities than you would expect. So the conductivity may be low, but if you take the conductivity and divide it by the concentration, that gives you the mobility or the velocity. And so that can be surprisingly high, despite the fact that the conductivity appears low. For sure, there's not going to be as much signal to noise as well in a system like that. But in our experience, we've certainly measured down in these electrolytes, we've measured down into the 0.1 molar range. And then, for calibration purposes, people have done many measurements on tens of millimolar systems. So I think it's possible, but depends on how fast the micelles move, is really what it comes down to.
Okay, thanks. Another question from Walt Musevsky, who says, why isn't the solvent drift driven by both cations and anions?
Yeah, so that's an excellent question. And in a lot of lithium-ion battery electrolytes, the role of the solvent, ultimately it's dissolving the salt and really coordinating quite strongly with the cation. So there's a lot of systems, I would say the majority of systems, where the cation solvent interactions are really strong, and the interactions between the solvent and the anion are not particularly strong. And of course, you can maybe, I didn't show the structure of the TFSI anion, but it's a very bulky anion, and the charge is very delocalized. So there are definitely other systems, and people have also tried to form or design electrolytes where the anion moves very slowly by intentionally interacting the anion and the solvent, or using additives to slow the anion down. And if you, it would be very interesting to look at a system like that and see if the solvent velocity or the solvent mobility might be negative in a case like that. So I think that would be a great study.
Okay. Another question from me. Have you looked, or do you plan to look at any of the systems where cation anion triplets have been reported, and would you be able to see kind of an opposite phase, a negative velocity?
Yeah, definitely. That's a great question. And if I had a conclusive proof of that, I probably might have showed it, or would be in the process of writing it up. But we are definitely interested in doing that. Part of the problem is that we expect a lot of those clusters to form in the very concentrated regime. And when you go to these very, very concentrated systems, then you start running into problems because everything is moving very slowly. You have a lot of signal, which is great, but and the conductivity might be decent, but because you have so many charge carriers, proportionally each charge carrier is moving relatively slowly. Everything is very viscous. So the velocities become small, difficult to measure. One of the things that we are doing now is to move to stronger gradient systems where we can actually apply much stronger gradients and actually detect a phase shift, where we should be able to see that. So stay tuned. We have hopefully some new PFG equipment that will enable that. Yeah.
Okay, great. Looking forward to that.
Yeah.
I had a question from Anna Gunnarsdottir, who says, hi, David. Thanks, great talk. Are you limited to study certain electrolytes, i.e. does the T2 have to be long enough?
Oh, that's a great question. And hi, Anna. Yeah, yeah, I would say that, well, so typically when you're doing these types of PFG or eNMR measurements, for sure, you want to have a T2 that's long enough, but also it usually matters more about the T1, because in the double stimulated echo sequence, you're T1 limited. So, we've been fortunate in that all the nuclei that I've looked at so far, and in the systems that I've looked at, both T1 and T2 have been long enough. I would say that in other systems I've looked at, once the T1 drops below, 100 milliseconds or gets very short, then it really proves a challenge to be able to get enough signal by the end of the sequence. And that's one of the challenges in looking at quadrupolar nuclei, I think. Lithium is quadrupolar, but for the most part, we treat it as though it's not. But things like magnesium, zinc, sodium, those are going to be more challenging. I think it's possible to extend the technique to those systems, but it's going to require some ingenuity to be able to design pulse programs to do that.
Okay, thanks. And on that point, do you think there's any possibility of extending to solids eventually?
Yeah, I would. Yeah, this is great because I sort of feel a little bit adrift. I'm not connected to the solid space anymore, but I think for sure, I think as long as you've got motion that's fast enough, and there are definitely plenty of fast ion conductors where the conductivity is known to be greater than in liquid and polymer systems. So that's not necessarily a problem. But I think you may be limited by T1 and T2 effects in those systems, so that might be the sticking point. But I would love to be able to move towards solid systems. The other thing about solids is that typically they're naturally single ion conducting anyway, so you only have one particular species you're interested in. But that's it's not necessarily the case. Sometimes you have mixtures of cations in some systems, and I think as long as you can have a system where the mobility or the velocities are fast enough, and you've got a gradient system that's strong enough, able to apply very strong gradient pulses, I think it should be possible in the future.
Can you apply larger voltages to a solid potentially?
That's a good question too. I have really not thought about that very much, but you would think so. Yeah, you would think that if you caused any kind of degradation, at least it's not going to, kind of come into the middle of your where you have the coil and disrupt the measurement that way. So yeah, that might also allow you to go to really high voltages. Sounds like an interesting experiment. Yeah.